So, chapter 19 is going to connect us to some other ideas of physics from 7a that we had last semester. And we're going to sort of expand on some of those ideas from 7a, specifically talking about heat and heat transfer. So I think a lot of us kind of think of the idea as heat as like, oh, I'm hot. Like maybe I have heat. Like it's like something that I'm possessing that's making me hot, okay? Just keep in mind that as we talk about heat, that's not at all what we mean. Notice the first two words up there after the definition of heat. We're going to say that it is energy that's being transferred from one substance to another. So you can't really say that there's a certain amount of heat in an object or in a different object. Instead, as I put two objects in contact, imagine this energy that's in transit. The energy that's in transit between one substance and another is what we're going to refer to as heat. Specifically, this is energy that gets transferred between substances when they're not at the same temperature, when there's a temperature difference between the two, and there's an energy transfer. That energy that transfers from one thing to another is something we refer to as heat. This might remind you of the concept of work in Physics 7a. Work is kind of a different twist on the same thing, right? When I have work that's being done, that's also an energy that's transferred, right? I could do positive work on another object, and I could put mechanical energy into that other object and say, give it more kinetic energy, make it speed up. Well, that energy that gets transferred is just something we call work. And instead of a temperature difference doing it, it's a force that does it, okay? So we've got two different types of energy transfer. Go Tigers, once again. You're getting that every time I walk by. Two different types of energy transfer. One that happens because of a temperature difference. We call that heat. One that happens not because of a temperature difference, but instead because of a force, we call that work, okay? So in a lot of ways, this is an extension of our concept of work from last semester. So there are a couple of things I should add to this, and I think I have way more room on this particular slide than I perhaps need. Let me switch my notes. First of all, we're going to use Q to represent heat. And since it is a form of energy, it's specifically this energy that's in transit, the unit here will be joules. Q will be the symbol, our unit will be joules. There are a couple of other units that are often used, and you'll see these down here below, the calorie and the kilocalorie. Of course, kilo would just be 1,000 calories, so there's not too much to talk about there. But these are in terms of the concept of temperature difference. So you can see that the calorie is the amount of heat or the energy transfer required to change the temperature of 1 gram of water by 1 degree Celsius. Personally, calories, like that feels a little chemistry-ish to me. And anytime we start to border on chemistry, it's like, yeah, I start to kind of clam up a little bit and things sweat and I start to hate myself some. So does anybody feel that when you're around chemistry? Yes, thank you. 2 of us are on the same page. I hate to ask the next question. How many of you feel that around physics? There you go. You can raise your hand. It's fine. Yeah. A few. I saw it was like, oh, I shouldn't do that. I'm going to keep my hands down. So, yeah, I get it. There's topics that none of us like. But I can't wait till chapter 21. 21 is fantastic. We'll get there eventually. So, calorie and kilocalorie. I should point out that this particular temperature change of 1 degree Celsius, this is defined as being a temperature change between 14.5 degrees Celsius to 15.5 degrees Celsius, to be specific in defining the calorie. The calorie doesn't suffice from a physics standpoint. So how do we get calories over into joules? Well, it turns out, Joule gets his name on the unit because of Joule's experiment over here, all right, where he did what we would call the mechanical equivalent of heat. In other words, trying to make a connection back to more physical quantities. The mechanical equivalent of heat. So, he took a fluid, as you can see there, that's contained, and there's these paddles that are inside, which was connected to a pulley and then over to a weight that could simply be dropped. Okay? We know something about dropping a weight. We know how much change in mechanical potential energy happens there, gravitational potential energy. We know that that change in potential energy is equal to m times g times h as the weight falls from there to ground level. Okay? Well, that falling weight, in turn, did work on the fluid by turning the paddles. While doing this, he carefully monitored the temperature of the fluid and watched how much it increased as a certain amount of work was done through that change in potential energy. Okay? So a connection between a temperature change and an amount of physical work that's being done. And he found this particular connection, that 4.186 joules was equal to 1 calorie. 4.186 joules was equal to 1 calorie. So through this process, we could say that Joule extended the work energy principle And again, the work energy principle would be the part of this that you learned last semester. And he allowed it to include heat. And all of this work, we could say, led to the law of conservation of energy. Because now we were including all the types of energy we could observe that were moving between substances and not just dealing with mechanical energy. Led to the law of conservation of energy, and we'll talk about that a little bit more later in chapter 19. Okay? So we've got the concept of heat. Everyone good there so far? Looking for hands? Nobody? Anything? We've got heat that's energy being transferred. We know how that connects a little bit perhaps to temperature changes. What we haven't talked about is like, what is this energy that is inside the material that somehow gets transferred to other substances and changes its temperature? This energy is what we might call internal energy. It's the energy that's in the substance itself. Sometimes this is referred to as thermal energy. And this is the sum of the energy of all the molecules in the substance. And that definition will allow us to connect it back to the last chapter. The sum of the energy of all the molecules in the substance is what is known as the internal energy. So, let's rewrite out a few of these definitions. So first of all, the temperature, don't forget, is proportional to the average kinetic energy of molecules. We have right above that a definition of the internal energy. We know that heat is an energy transfer. Just to pull everything together here at once. And we should point out also that the direction of heat flow is based only on the temperature, not the internal energy. Internal energy, also known as thermal energy, it's if we add up all of the energy of all the individual molecules. Temperature is related to what the kinetic energy on average is of individual molecules throughout the substance. Heat is about the energy being transferred because of a temperature difference. And keep in mind that which direction the energy flows, the heat flows, is based on the temperatures of the two objects, not how much energy is contained within them. Now, if you're thinking like, aren't those kind of the same thing? Let me point out somehow that they're not. So let's say that we have this particular iPad and it's at a particular temperature. And let's say that perhaps we also had, two iPads that were bonded together that were at exactly the same temperature. Okay? So we've got two of those. If I touch them together, so I've got the one iPad and then this block of two iPads at the same temperature, well, they're all at the same temperature, and according to the zeroth law of thermodynamics, there's not going to be any temperature change because they're already at equilibrium. In other words, there will be no heat flow or energy transfer from one to the other. However, the two iPads clearly has more molecules than the one iPad, right? So if I were to add up all of the kinetic energy of all the individual molecules, the two iPads is going to have more internal energy than the just one, even though they're at the same temperature. So the fact that one has more energy overall doesn't allow it to transfer energy. It's only whether they have a temperature difference between them. Do you see the difference? Okay? Internal energy is about adding everything up. So let's get to some equations. Let's see. First of all, based on what we said above, we could just describe E internal as the number of molecules times the average kinetic energy of those molecules. So that means this is equal to N times 1/2 mv squared average. And we also know that, this part is equal to 3/2 K times T. So the kinetic energy part is equal to 1/2 mv squared or 3/2 KT. So let me rearrange that a little bit, and that gives us one of our equations for the internal energy. So we got 3/2 times NKT. And it's important that that capital N is in there. Maybe that'll help you remember that it's about all of the individual energies added up, because we're multiplying by the number of molecules that are in the substance. Let's see, but don't forget that K is also equal to R over Avogadro's number. So if we plug that in, we can get something a little bit different. So that's going to be 3/2 times nRT over Na. And then that thing, N over Na, is just the number of moles. So that's nRT. Notice that connects internal energy back to temperature, which I think should make sense based on everything we're saying. So internal energy is dependent on temperature. Not just temperature, though, but how much you have there. Okay? The internal energy is dependent both on the temperature, that relates to the kinetic energy of those individual molecules, as well as how much of the substance is there. Questions, comments, thoughts, anything? Yes. Similar principles, but it quickly gets complicated. We will hint at a little bit of that, but we won't go into it in detail here. Okay? One more thing that I should add to this, and this hints a little bit at what you're asking. Everything that we're dealing with here, this is about monatomic gases. In other words, this particular kinetic energy that we were talking about, this is the translational kinetic energy. Remember, translation is about movement from one place to another. So we're only talking about one type of kinetic energy in this entire discussion, and that is the motion of a molecule from one place to another. As soon as I start to add additional molecules, so if we had a diatomic gas, well, now all of a sudden I've got two atoms that are bonded to each other. You can imagine that we can have additional types of kinetic energy. It might be possible for that molecule to rotate, so you could have rotational kinetic energy. It might be possible for them to move back and forth a little bit, which would give me vibrational kinetic energy. So as soon as I move up from monatomic gases, all of this gets more complex. So we should say if there's more than one atom, then you could have rotational and vibrational kinetic energies. as well. And we'll address that just a little bit in a later chapter. So that brings us finally to a connection between heat and temperature change. I am going to take a stab in the dark and guess that you have definitely done this in a chemistry class. Let me write an equation and see if more of you nod. Q. So our heat transfer is equal to M times C times the change in temperature. Chemistry class? Never before. Who says never before? You can hide that hand if you want to. Anyone's like, that doesn't look familiar. Okay? There will be a few, and that's okay. But I'm going to try to speed up through this particular part because a lot of you have seen this before. So this particular equation tells us how much heat must be transferred to change the temperature of a substance, whether to increase it or decrease it. It's based on how much mass is there, but also on a property of the substance known as the specific heat. Let's see. The specific heat here will be in units of joules per kilogram Celsius degree. And you can see right below, it tells us something about how much heat is necessary to cause a certain change in temperature in a substance. So if something has a higher specific heat, I have to either pump in a lot more heat or take out a lot of heat to get a very significant temperature change. Things with low significant heat, it doesn't take a whole lot or low specific heat, it doesn't take a lot of removal or adding to change their temperature. Closely related to this is another concept known as heat capacity. I should just say that these are related like this. The heat capacity, big C, and I'm going to make that extra big so you don't get confused, is equal to M times the specific heat, little c. Okay? So a subtle difference between these two, they're both telling us something about how much heat has to be added or taken away to change the temperature of a substance. The specific heat, though, is like particular to the type of material, but the heat capacity is not only about the type of material, but how much of it you have, okay? So in other words, you might be able to look up a table of specific heats for a bunch of different things, for like, water, for iron, for copper, for iPads, I don't know, okay? A big list of specific heats. And those numbers are going to be all about just like a standard number for that particular substance, but they don't take into play how much of it you have. Because clearly, if I have a little bit of copper versus a lot of copper, well, I'm going to have to put more heat into the large mass of copper to change its temperature. So specific heats are like standard values for a substance. Heat capacity includes the idea of how much of that substance you have. Let's see. I should point out that the specific heat is a little bit temperature dependent. But will be constant enough over a relatively small temperature range. We're not going to worry about the temperature dependence of specific heats. We will assume that whatever value we're given for a substance, that is a constant value, and we'll use it for that substance. So finally, a few questions for you people. Read, and when you think you have it, vote with your fingers. Looking for votes. Okay, that looks good. Looks like most of us are on the same page with 4. Notice it said they're made of the same material. So that means C is going to be the same for both. So it's going to be about how much of the material is there that affects how much temperature change you have. Less of it will give me more temperature change for a given amount of heat exchange. How about this one? 2 different objects receive the same amount of heat, so Q is the same, which is not a reason why they may end up having different delta T's or different temperature changes. vote when you have it. Some of you have voted. Many of you have not. Some of you are asleep. Okay, looks good. So let's see. Different masses will affect things. Different specific heats will affect things. Different initial or starting temperatures isn't going to matter. It's about you're still going to get the same amount of delta T no matter what temperature you start at, assuming we're not talking about ridiculous temperatures. All right. Number 3, 2 equal mass liquids initially at the same temperature are heated for the same amount of time over the same stove. So you might assume that Q is the same for these two substances. You measure the temperatures, find that one liquid has a higher temperature than the other. What does that tell you about their specific heats? Which one is higher? Higher specific heats are harder to change the temperature, right? So the one that has the higher specific heat is going to be the one that has stayed cooler, all right? So number 1 there. And then finally, the specific heat of concrete is greater than that of soil, as if that's something that just everybody knows, all right? A baseball field with real soil, fantastic. I don't know why. And the surrounding parking lot are warmed up during a sunny day. Which would you expect to cool off faster in the evening when the sun goes down? Again, that's going to have to do with their specific heats. Higher specific heat is harder to change its temperature. So which one is going to cool off faster? The one with the lower specific heat. So in that case, the baseball field with the real soil. All right. It is 3 o'clock. Let's all take a deep breath. We're not quite done for the day yet. I have a slide I'm trying to get to, and if we get there early, we get there early. If we don't get there, well, then we just go to 3:30 and see what happens. But thankfully, maybe it's not as far along as it could be. Okay? Anybody have any questions so far? Anything? Anybody want me to stop doing that? Yes? Wow. Like all 3 of you right here, like immediately were like, we will punch you if you continue. Question on the other side. If we had a massive increase in temperature, different parts of that temperature range actually might have a slightly different specific heat. We're not going to worry about those cases in here. You can assume it's a constant value for any temperature range we deal with. Yes, if I understand your question correctly. Yeah, so Q goes in, and that results in a change in temperature. If the temperature changes too much, by the time you get to the end of that, C might have changed a little bit, so your calculation could be a little off. Okay? Which brings us to calorimetry. Calorimetry. How many of you have done a calorimetry lab at some point? Not as many hands as I thought. I thought every single one would go up, but every single one didn't go up. Should I try that again? Who has done a calorimetry lab at some point in your life? Who has done calorimetry calculations at some point in your life? Who has no idea what... No, I'm not going to ask that question. Calorimetry. Calorimetry, hard to say, is a specific type of problem. I'm going to kind of half do a couple of example problems here just to make sure we're all on the same page, but I'll let you kind of flesh out the details yourself. Calorimetry is a way to track how much heat is being exchanged between items and sort of watch what happens to the temperature and also any phase changes between the objects. So what we're going to do is take some objects and isolate them. We're going to put them together in such a way that they can exchange heat with each other, but no heat can get in or out. No heat can get in or out. So that means that if one object gives up some heat, one of the other objects in the system has to accept it. It can't just vanish, and I can't just create more heat or have more come in from the outside. So any heat transfer occurs between the items that are in the system. And essentially what we're going to do after we put these objects together, we're just going to let them come to thermal equilibrium, meaning we're going to let that system that we've isolated come to some common temperature. Every object we put in the system will be at the same temperature. So let's see. What is a couple of things that I wanted to say about this? One equation will kind of rule the whole thing. I've got a lot of space here. I should use it. Sum of Q. Yeah, this is ridiculous. In other words, if I add up all of the heat exchanges, some are going to be positive, some are going to be negative because some objects are accepting heat and some objects are giving up heat. But if nothing can get in or out, if I add them all up, I should get 0 for a calorimetric system. So for instance, really quick, a very quick example. We've got some water, and it's poured into an aluminum can at a certain temperature for both of those. We're asked to find the final temperature of the system, assuming no heat is exchanged with the surroundings, so it's an isolated system. It's an isolated and closed system. So in this particular situation, we've got water that is at a higher temperature than the aluminum can. So you can just imagine if I put these two things together, well, they're going to reach some temperature in the middle. The thing that's hotter is going to transfer heat over to the thing that's cooler because, again, it's based on temperature, the direction that the heat flows. How weird would it be if it went the other direction? What a strange world that would be if you put hot and cold items together and heat didn't go from hot to cold, but went from cold to hot. That kind of breaks my brain a little bit to think about it, right? That would be almost like if there was a huge block of ice up here and I'd be like, oh, huh. Well, I think I'd like to get hotter. So I touch the ice, and I suck energy out of it, and all of a sudden I'm sweating, but the ice gets colder. What a weird world that would be to live in. So clearly things don't naturally occur that way. We know that our final temperature will be somewhere between 15 and 32, just because of the direction of heat flow. So we could write a couple of things down. We could say that, first of all, we know that the water is going to cool, and the aluminum is going to heat. Al heats. Anybody in here named Al? Because I'm going to call the aluminum Al for the rest of this problem, just because it amuses me. The water will cool, and Al is going to heat. For both of these, we're looking at temperature changes. Neither of these are anywhere near a phase change, so we're not going to have to worry about that at all. So for both of these, MC delta T will describe the connection between how much heat is gained or lost and how much temperature changes. So what we can do is use our calorimetry equation, delta Q, or the sum of Q is equal to 0. And we can write down an MC delta T term, and I'll write this out in some detail, for the water cooling. And we can add that to an MC delta T term for Al heating. And those have to add to give me 0. Keep in mind, at this point when I'm dealing with just temperature changes, I don't really have to worry about signs. The delta T terms, depending on whether it's warming or cooling, sometimes you're going to get a negative sign out of there automatically. So if something is giving up heat, if heat is leaving the substance, it's automatically going to give you a negative sign because the final temperature is going to be less than the initial temperature. So I can just add everything together and let the equations sort of take care of themselves. So what we might do is write this out in a little more detail. We could say that the mass of the water times the specific heat of the water times T final minus T initial for the water plus the mass of Al times the specific heat of Al times T final minus T initial for Al equals 0. And you've got everything in there except for T final. I'll let you work out the details of that. But, I don't even have the answer here. T final equals something. Yeah, I'll let you solve for it because I don't have the answer. No, it's just not here. Yep, don't have it. Didn't write it out. Anybody already calculate it? Want to tell me what it is? No, I didn't think so. All right, something to work at a little bit later. You can confer with each other and see if you get at the same result. Do you see how the problem sort of sets up, though? Things are changing temperatures. I need one term to account for every object in the system that's changing temperature. Okay? So, how about a quick calorimetry problem of your own? This one you should be able to do really sort of without any calculation, just by using the ideas that we've talked about. Hopefully you can quickly rule out these two extremes, I think. And perhaps as well, just based on their relative masses, it would make sense it's not going to end up in the middle. So the question is, which way is it going to tend toward? You've got more of the cold water, so it makes sense that it would be down this direction. You could also just look at that based on ratios. It's a 4-to-1 ratio of masses, so that means the one that you have less of should move 4 times as much, or 4-to-1 ratio as much in temperature. Let's see, something here that might take a little bit more calculation. Who's got answers? Any votes? I see a few twos. Yeah, I like 2. This is all about their relative specific heats. So I have the same amount of water and silver. The silver is hot, the water is cold. The water is not going to want to change temperature, though, because of its relatively high specific heat. So it's almost like it's got more temperature inertia. You have to drag its temperature up. So instead, the silver is going to cool rapidly or more than the water, which means we're not going to end in the middle. We're going to end more on the water temperature side of things, so somewhere between 0 and 50. And then this one, actually, we haven't talked about thermal conductivity, maybe later, but that slide shouldn't be there, so we're not going to worry about it. Ha ha ha. Which brings us to phase changes. We're going to do the same thing, but just add in the idea that sometimes the temperature change may cross over a phase change barrier. I should change this. This should say latent heat, which is the heat transferred as the substance changes phase without changing temperature. The amount of heat that's added or lost while the stuff is either breaking down or sort of assembling into bonds to change phases from one to the other. Just keep in mind that temperature is not changing when this happens. So we've got a few of these that we could do. In general, we could say that Q is equal to M times L. And L can have different options. It could be the latent heat of fusion if you're dealing with a solid-liquid change, liquid heat of vaporization if you're dealing with liquid gas. We could even have latent heat of sublimation if we're dealing with solid gas, but I didn't solid to gas, but I didn't list that one up there. Notice the equation is just how much you have, how much matter, how much mass, and then this term that tells you how difficult or how much heat is required to change the phase of the substance. Q is equal to M times L. To give you a feel for how all of this works together, we could look at water. So this is a graph for water. Notice on the y-axis we have temperature, and at the bottom we are adding more and more heat to the substance. And I think this points out something a little bit interesting. We're going to start with ice. So we've got frozen water that's at negative 20 degrees Celsius. Keep in mind, you can't just melt ice that's colder than the freezing point of water. I have to put heat in and raise the temperature of the ice to the freezing point before anything can happen. So you can see that as we add some heat, eventually we get the temperature up to point A, which is at the freezing point at 0. So this first little line, if we wanted to find exactly how much heat it is, we would use MC delta T for that portion. Once we get to point A, once we're at the freezing point, this is not a situation where I dump heat in and it's like, oh, it starts warming even more and it starts melting. It's going to stay at that temperature until you melt all of the ice. It all has to be gone before it can increase in temperature again. So you can see that the line goes flat and we stay at 0 as it melts and we add more and more heat. And here, the equation we would use is QF for fusion is equal to mass times the latent heat of fusion. That tells us how much heat is required to melt it. Notice, I had to put more heat in to melt the substance than I did to change its temperature from negative 20 up to 0. I think logically that just makes a little bit of sense, right? I had to take that solid and actually break those bonds down to transform it from solid into liquid. Some more energy is going to be required for that. Then, as we go from B to C, we're adding additional heat. You can see that we're raising the temperature, so MC delta T would apply to this. But the C is now different. This is C for water, and down here we had the specific heat for ice. So the only thing that's changed there is the type of specific heat that you're using. MC delta T. And then once we get to point C, well, we're at 100 degrees Celsius. It'll begin to vaporize, and it's going to take some energy to do that. Again, now it's going to take even more energy, more heat, more work has to be done to not just loosen the bonds to make it solid to liquid, but now we have to rip those molecules apart. Well, that's going to take quite a bit of heat. Notice how long that line is before it begins increasing in temperature once again. So you add heat, 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 you add heat. It stays at 100, and then once all those bonds are broken, eventually that steam can start rising in temperature above 100. Yeah. What variables? What state variables do you have in that particular case? What do you say? What state variables is remembering? Yeah, between A and B. I think that's just about, at that point, we've got both ice and water. So we just have a mixture of the two. That's what's remembering how far along we are. Yeah.
What's exactly the difference between, like for example, the ice that is let's say 10 degrees Celsius, 20 degrees Celsius. 10 degrees we have more loose connections between the molecules.
At the higher temperature, there would be more motion of the molecules. So while they're still bonded to each other, you could think of them as having more motion about their equilibrium point.
Is there like a special force that makes it solid or liquid or gas?
Oh, there's a lot of chemistry going on there. I'm going to have to refer you elsewhere for that one. That's more than we want to get into in here. I'm sorry. Anything up there that's bothering you still? Yeah? The potential energy of the molecules, yeah, that would be different. But at that temperature, the kinetic energy is the same. The total internal energy? See, here we're dealing with solids and liquids, so the things that we talked about regarding energy before was just dealing with a monatomic gas. So the energy calculations there, they'd be different, but they're complicated. There's something we're not going to cover in this class. Who else? Who else finds that long, flat line kind of intriguing, going from liquid to gas? Yeah? Watch out for steam. You know, just sort of in general. You're like, oh, my water's boiling. Like, well, you've got the boiling water and then you've got the steam right above it. Once it became steam, a lot more energy went into that. So it's going to burn you worse. So if you have a choice between really hot water and steam, I don't know when you're going to face this choice. Maybe you reach a fork in the road and you're just like, I have to go forward. That's full of steam. That's full of 90-degree water. Take the water, okay? It may seem like it's only a 10-degree difference, and it is, but the energy difference is rather dramatic, all right? Which brings us to, let me see what I've got left here real quick, see where we're going to get to. 1, 2, 3, 4 more slides, and then we're at our breaking point. So we will finish just a smidge early, but not a whole lot. One more calorimetry problem that I'll get set up for you, one that involves phase changes. Here we've got a beaker. Notice it doesn't say what the beaker is made of, so we've got an unknown substance, which leads to the question all the way at the end. What is the specific heat of the beaker? We don't know anything about it, so we're trying to find something out about this beaker. It is filled with some water, and they are in thermal equilibrium already, so the beaker and the water are at 22 degrees Celsius. And then we're going to put some ice that was initially removed from an ice-water mixture, meaning that it is at 0 degrees Celsius, and drop that into the other water that's at 22 degrees and let it come to thermal equilibrium. So we've got 3 different substances here that are doing a variety of things. So let's make a little list of these. First of all, we know that the beaker is going to cool. Once I put the ice in there at 0 degrees Celsius, well, that 22 degrees should come down. The beaker is going to cool. Number 2, the water that's there is also going to cool. It should drop in temperature as well. Number 3, you might expect the ice to melt. And I'm going to tell you that all of the ice is going to melt just based on the fact that there's, well, a little bit of ice and a whole lot more mass of both the beaker and the water. You could do some initial calculations just to see how much energy would be required to melt the ice and double check that that's true. But I'm going to tell you in advance that all the ice is going to melt. And then number 4, I'm going to have some water that came from the ice that is going to warm up. So keep in mind, we've got some additional water now that was going to go from 0 up to some final temperature. My bad. It says the final equilibrium temperature is 17 degrees, so we know all the ice has to melt. So the beaker cools 5 degrees, the water cools 5 degrees, the ice is going to all melt and then go from 0 up to 17 degrees. So we could write all of those down. So it's 22 to 17, 22 to 17. This is going to all happen at 0 degrees, and then this is going to go from 0 up to 17. So there's going to be 4 different terms in the equation, 1 for each of these. All the temperature changes, again, are MC delta T. The ice melting, number 3 there, will be M times LF. Okay? So you could say that the sum of all the Q's has to be 0. And let me just write this out in detail, and I'll tell you the answer, which I actually have this time, and you can calculate it yourself later. We're going to say that we have the mass of the beaker times C for the beaker times T final minus T initial for the beaker, plus the mass of water times C of water times T final minus T initial for the water. And then for ice melting, there's nothing in M times L that's automatically going to give me a positive or negative sign based on the direction of heat flow. So I need to think a little bit about whether this one should be positive or negative. If heat is going into something, we call that a positive heat. If heat is leaving, we call that negative. So in this particular case, this is going to be a positive term, which will be the mass of the ice times LF for the ice. Heat is going in and melting that substance. And then finally, we've got the mass, what to call this one? I can't call it the mass of water or the mass of ice, although actually all that's going to be the same. So let's just call it the mass of the ice once again. But now this is going to be the specific heat of water times T final minus T initial for this, what to call it? We'll say the water from ice. And all that has to add to give you 0. You're given a bunch of numbers. The only thing in there that's unknown is the specific heat of the beaker, which you should be able to solve for. And I will tell you it comes out to be, I think, 9792.5 in units of joules per kilogram degree Celsius. Use that for practice later. The question is, do you understand how the problem sets up? You could handle calorimetry problems with 60 substances all put together. We should just make that like exam 1, right? It's like 2 hours of a calorimetry problem. Whew. I don't know if that sounds like fun. Too many places where it's like one sign error and all is lost, and that would just be terrible, all right? So let's see. Let me ask you, I think I've got 3 questions here. We'll do these, and then we will call it a day. We put 1 kilogram of ice together with 1 kilogram of water at 2 different temperatures. What is the final temperature in this case? And I'll use both of these to show you how you can do some initial calculations to give you a feel for what's going to happen. First of all, how much energy or heat would be required to melt all of the ice? Well, I'm just going to use the units that they already have there. Notice LF is given in 80 calories per gram. So I could say that Q is equal to mass times L. So that's going to be 1,000 grams times 80. So 80,000 calories would be required to melt all of the ice. That energy has to come from somewhere, and the only place it can come from is the water dropping in temperature. So let's say if the water were to go all the way down to zero, how much energy could it possibly give up? So we'll say to cool the water, Q is equal to MC delta T. Well, I've got 1 kilogram, so that's 1,000. C is just 1 in these units, and delta T is 50. Well, notice that's only 50,000 calories. We don't have enough energy in the water to melt all of the ice. So what does the final temperature have to be? It will All right, so the first law of thermodynamics. We did the 0th law. We're going to talk a little bit about the first law and some processes in which we use the first law, and then I'm going to stop for the day after we do that. The first law of thermodynamics. So right there at the top, something that we said in the last class, 2 different types of energy transfer. We added the idea of energy transfer because of a temperature difference, which we said is something known as heat. Okay? We even looked at that and how to actually calculate how much heat is transferred in the case of a certain temperature difference. And we had the equation MC delta T, and we did all of that sort of work last time. And all of you really enjoyed it, I could tell. Yes, right? Okay, you were all like, this is fantastic. I love finding out something about specific heat. You all seemed terribly thrilled. So we did that. That was adding to a concept that you already had from Physics 7a, which was when I have a transfer of energy that has nothing to do with the temperature difference at all. Instead, it's mediated by a force, which is something that was called work, all right? Putting these two things together gives us a full picture of conservation of energy, and all of that together is what's known as the first law of thermodynamics, which we can write like this. We can say that the change in the internal energy of a system, and we're going to say specifically this is a closed system, nothing is getting in or out, is equal to Q minus W. Q minus W. The change in the internal energy of a closed system is equal to Q minus W. So, notice that is a positive Q on the left. So this is officially the net heat added to the system. You would just flip it to be negative if heat is leaving the system. And then on the other side here, we have a negative W, which means this is the net work done by the system on something else. And if work is done on the system instead, well, that would get flipped around and become positive. So there's some big statements right underneath that. I kind of like it. One of the great laws of physics, which I feel like it should be in a bigger font now that I say it. Don't you think? Yeah, it really should be. One of the great laws of physics. Literally, we've never observed an exception to this, ever, anywhere, in all the observations around the universe. And technically speaking, this is just a broader version of what you did last semester with conservation of mechanical energy alone. This is a bigger statement dealing with conservation of energy as a whole, because we're including heat at this point. Let's see. I should add a couple of other statements down here. First of all, if the system is isolated, so not just closed, but isolated, we could say, and by the way, with closed, we're meaning whatever matter is in there is the same amount. Like that is constant. Nothing gets in or out. If the system is isolated, then, well, it's not doing any work and no heat is getting in either. We could say that the change in internal energy is equal to 0, which means Q would be equal to W in that case. If the system is isolated, change in internal energy is equal to 0. I should point out that Q and W are involved in processes. Remember, we said that heat is about energy that's in transit. It's moving from one object to another. Well, work is also a transfer of energy. They don't have to do with what state the system is in. So Q and W are not what we would call state variables. On the other hand, the internal energy is a state variable. It's about how much energy that system possesses at a certain point in time. So Q and W are about things entering or exiting, right? Different types of energy. And internal energy describes part of the state of that particular system. So we're going to use this and look sort of broadly at 4 different types of thermodynamic processes and how we would apply the first law of thermodynamics to those. Once I do those 4 processes, you can see number 1, number 2, and then number 3, which is actually 2 of them. That's the end of the week, okay? So can you, rally your attention span for 3 slides? Do you promise? Oh, are those lies? No? You can do it? You can do 3 slides? As far as you know, though, I'm going to take a half hour per slide. So you just agreed to be here till 4:30. So congratulations on that one. Number 1, isothermal processes. Isothermal processes. By isothermal, we mean that the temperature is not changing. So delta T is equal to 0. And we're going to specifically look at these under the guise of ideal gases, all right? So if I look at the ideal gas law, PV equals nRT, well, if T isn't changing, that means this is equal to a constant, which looks a whole lot like sort of the first gas relationship that we looked at in the list back in the last chapter. We just have P times V is equal to a constant. And it is this relationship that leads to graphs that look like what we see on the right, on the PV diagrams. So each one of those red curves represents a temperature. So if I move from point A to point B on that graph, like the pressure and volume are changing, but the temperature is not along that curve. If, on the other hand, I go from A prime to B prime, that's a different but lower temperature as I move from one state to another with different pressures and volumes. But the temperature is not changing. Each one of these lines, just for reference sake, are known as isotherms. They are lines on a PV graph that represent no change in temperature. And we could say that going from A to B, or from A prime to B prime, or the other way around, are isothermal processes. So how does this happen? We are going to look at an instance like you see on the bottom left. We are trapping some ideal gas in a cylinder, and the top of that cylinder has a movable piston that perhaps has some weight, but no friction, like it can easily move up and down if the gas were to expand. We're going to take this whole thing and put it in some kind of like a constant temperature bath. That sounds nice, doesn't it? Not necessarily. You don't know what the constant temperature is. Could be a terribly uncomfortable thing. What I'm trying to say is that we're trying to hold this system, the gas, the piston, the cylinder, the whole thing. We're not going to let it change temperature no matter what we do to it, okay? The constant temperature bath is perhaps controlled by some other apparatus that maintains the whole system at a constant temperature. And then what we're going to try to do is from outside this whole thing, we're going to add some heat and see what happens. So we're adding heat to the ideal gas in some way. So maybe this whole thing is in a constant temperature bath, but like right under the cylinder and piston, maybe there's a little heating element of some kind where we're going to input some heat into the ideal gas. So what has to happen is that, well, all of a sudden, the motion of the molecules in the ideal gas has to increase. More energy, more kinetic energy, more velocities, which means they are going to begin to push on the piston with a greater pressure, okay? So they're essentially going to push the piston up some distance and do work, physical, mechanical work, by moving that piston. So we could say we add heat, simultaneously keep temperature constant, and the gas will expand and do work on the piston. So what does that look like in terms of the first law of thermodynamics? Remember, delta E internal is equal to Q minus W. Yes, everything is out of order here. Just deal with it. It'll be fine. I should put the next part over here. Sideways, and then we'll go around upside down. No, I'm not going to do any of that to you because that's ridiculous and dumb, and I would not do dumb things. Yeah, I'm not talking about myself all of a sudden. By the way, I'm a child. I've learned. It's like, you're 20 and you're like, boy, we just goof around all the time. And you think those 40-year-olds out there, they're adults. And then you become one, and you realize, we're still children. We just fake it in public, And I don't even fake it terribly well in public. But, if you hung out with me and my wife for a day, and we, actually let you see us in our normal habitat, you'd be like, children, such children. It's terrible. So anyway, delta E internal. Why do I confess these things in public? I don't know. Delta E internal. Don't forget from, when was it? I guess last chapter or earlier in this chapter, we said delta E internal is equal to 3/2 nR delta T. If temperature isn't changing, well, that means that the internal energy of the system isn't changing, right? No extra energy is happening there. So that means Q in this case is equal to W, which seems to agree with what we just described there down below, right? We added some heat, and that heat directly resulted in work being done on the piston, as long as the temperature isn't changing. Okay? Add heat, keep the temperature constant, gas expands, doing work on the piston. See, I told you. Just ignore me. That's isothermal processes, okay, in terms of the first law of thermodynamics. Number 2, adiabatic processes. Kind of flips things around the other way. We're going to hold something else constant. In this case, we're going to look at a system that instead of being in a bath that holds it at a constant temperature is just really, really well insulated so that nothing can get in or out. In other words, no heat is allowed to enter or exit, unlike the last one where we had the amount of heat going in changing and we kept the temperature constant, which means in this particular case, Q is equal to 0. Q is equal to 0. So what does that mean in terms of the first law of thermodynamics? Q minus W, that is equal to 0. So the change in the internal energy is negative? What might that tell us about what happens to the temperature? Looks like the temperature will drop. Okay? In this particular case, we have a gas that is adiabatically expanding. Or, over on the graph, this is going from point A to point C. So instead of staying on the isothermal line, by comparison, it sort of drops under it. Remember, on the PV diagram, the lower curves indicate lower temperatures. So it's kind of like we're moving from one temperature to another, or perhaps from one isotherm over to at least part of another isotherm. Okay? And of course, you could do this the other way around. If we did this the other way from C to A, in this particular case, we could say that we have an adiabatic compression. And if you're confused where it's expanding or where it's compressing, look at the volume, okay, and see which direction the volume is changing. Is it increasing or decreasing? For this to happen, we would have to have work being done on the gas, and the temperature would increase as we go from that lower curve to a higher curve. Isothermal, number 1. Number 2, adiabatic. The last two I'm barely even going to talk about, okay? Because there's just not so much to say about them. Isobaric and isovolumetric, weirdly enough, or isochoric, depending on which textbook you look at, apparently. It's isovolumetric in Giancoli. So noticing the word bar inside there, that's talking about pressure. So this is at constant pressure, and this one would represent a process that happens at constant volume. If I take a look at these over on a PV graph, they're just either a horizontal or a vertical line because, well, it's a graph of pressure and volume. If the pressure is staying constant, well, you've got this one. Oh, excuse me, I just drew that from the wrong line. Oh, I messed everything up. Make it stop. This one needs to go over here, and this one needs to go over there. The vertical line is at a constant volume. So if you're moving between points, it looks like that. You've got constant pressure or constant volume. We're not going to do anything else with this yet. Okay? If you were to go forward, let's see, not there, but 2 slides, you can see isovolumetric, isothermal, and isobaric all sort of come back into play. It's at that point I'm going to sort of show you how to use them. Okay? Just keep them in mind. We had finished off discussing not just the first law of thermodynamics, but some different processes, some ways to get from point A to point B, different pressures and volumes, using different techniques, different processes, different things staying constant and other things changing. What we want to do today is actually apply that a little bit and make a connection back to work, okay? So we're going to specifically start by looking at the work that's done as the volume of a gas changes. The work that's done as the volume of a gas changes. And I need to put in sort of a little space here. There we go. I guess that'll do. Because I need to say something just about the work itself before we talk about this first process that I have listed. So, work. You might remember from Physics 7a that work is related to force by an equation that looks something like that, at least in the differential form. If we're talking about a force that's causing some object to move a little bit of distance dl, we could express that as an infinitesimal amount of work. Force times distance, essentially. When I'm dealing with a gas, we can re-express force in terms of pressure. So we could say that force is equal to pressure times the area over which that pressure and that force is being exerted. So if you look at the case just underneath there, we've got a gas that's trapped in a cylinder, and we could say that it has a certain pressure, and above it is a piston, which it's going to push against with that pressure. And if it moves that piston just a little bit, then it's doing work on that piston. It's applying a force through the pressure, and it's moving it through some distance, okay? So we can take this and plug it into the equation above to sort of re-express the work equation in terms of pressure, and therefore we're dealing with a gas instead of dealing with sort of a discrete force, all right? So let's rewrite that as pressure times area times dl. And then what is the area times a little bit of distance? Sounds a whole lot like volume, right? So we could rewrite that as pressure times some volume. So re-expressing the work equation in terms of pressure, a little bit of work is pressure exerted such that the piston itself covers a little bit of volume. So if I want to find, say, the total work that's being done by the gas, we just need to integrate that, which means we're going to have an integral from some starting volume to some ending volume, P dV. All that to re-express work, not in terms of forces, but in terms of a volume change of a gas. Yeah?
So, in the first definition, the change in work is the force vector dotted with the differential length, but the F is equal to pressure times area, or pressure times area.
Yeah. I didn't write either of them as vectors, although sometimes there's an area vector that's perpendicular to the surface. You could perhaps express it that way. Hello, behind me. Did you bring snacks? You did. That's the entrance fee. Now keep walking. It's fine. Invisible snacks. No, invisible snacks are terrible. They're just not delicious. So let's take this. We're going to use this equation sort of repeatedly, okay? And we are going to take a gas from state A to state B. So take a look at the diagram on the right. State A is some pressure and volume, and we're going to change it to some new pressure and volume, which we're going to call state B. But we're going to follow the red curve. And on this red curve, as you see here, this is an isothermal expansion. An isothermal expansion, we're going from A to B, so the volume is getting larger. Notice it says quasi-static, which is a bit of a weird word that I think I might have just hinted at before, and I've definitely used it answering a few of your questions. So just let me explain what that means a little bit, because sometimes I think we get caught up in the process happening in a way that maybe this graph doesn't quite work. What we're doing as the gas expands is we're not just saying, let it expand, and all of a sudden the volume changes a big amount, okay? If that happens, you can imagine different points in the gas, are at different pressures, right? The top part might be really spread out, the bottom part not so much. So how can I plot, say, the pressure of the gas at any particular point in time there? So when we say quasi-static, you might imagine that literally The piston moves just a little bit such that the volume and pressure both change, but in a way that now I have sort of a new static situation. I'm not moving in such a way that now I have like differences throughout the gas. So we change it a little bit, establish a new pressure and volume, change it a little bit, establish a new pressure and volume, change it a little bit, establish a new pressure and volume. How many times can I do this? Change it a little bit, establish a new pressure and volume. Each one of those P's and V's is a static case, but we say it's quasi-static because like over a period of time, clearly there's a change. It's not a static situation. It's just made up of a bunch of individual static conditions. So, a quasi-static isothermal expansion of an ideal gas. Let's see how much work is involved as the gas expands. When it expands, it's going to move the piston, and it's going to do work on the piston. So, a couple of different things. First of all, we can say that if it's isothermal, there's going to be no change in temperature. Or we could say that T is a constant. And we're going to use this equation from right over here. So work is equal to the integral from, VA to VB, P dV. The key for all of these problems is we just need to know how P is changing. If we can find an expression or something for how the pressure is varying, then we're able to do the integral and everything is good. So in this particular case, it says it's an ideal gas. So I'm just going to use the ideal gas law, and we will express it, in terms of P such that we can write it into the equation. So now we have work equals the integral from VA to VB of nRT over V dV. Temperature is a constant, the amount of gas, and of course the gas constant are all constants, which means there's not a whole lot to do here. We've got nRT times this integral of 1 over V dV. And of course the antiderivative of 1 over V or 1 over anything is just a natural log. So we could say that the work done in this case is nRT times the natural log of VB over VA. That equation only applies when we're dealing with an isothermal expansion. The general equation, the integral of P dV, that applies for everything, but you're going to have different expressions for how the pressure is varying depending on the situation. To give you an idea of how it could be different, we're going to have another situation on the second slide. Okay? Take a look at the graph once again. Notice there's a shaded area there. We're doing an integral from A to B, so the amount of work is actually equal to the area under this curve that illustrates the process. So we could say that that area is the work. Are we okay so far? Or are we a little bit more sleepy at this point? I'm a little less sleepy because I started talking. So there may be a rule in here, sort of a conservation of sleepiness. That could apply in a physics classroom. As I get more awake, you're definitely going to get more sleepy. Question? If it were going the other direction, we would say it's the exact same amount because it's the same area. It's just negative in the sense that the piston is doing work on the gas instead of the gas doing work on the piston. Okay? So what if we keep these same two states, A and B, okay? But we're going to get there a different way. I could get from state A to state B and not keep the temperature constant. So what if we did something like this? And instead of following this isotherm, what if we instead started by keeping the volume the same, but allowing the pressure to drop? And then we kept the pressure the same while we increase the volume. We're still going to end up at the same pressure and volume. It's just sort of, we went maybe a roundabout way of getting there, okay? So we're going to follow these two lines this time instead to get from point A to point B, an isovolumetric process and then an isobaric process. Again, the area under the curve describing the process from point A to point B is the amount of work that's being done. But now I'm not including this area under the isotherm. The work is being done by the area under this curve. So you can immediately see from the graph that if I go this route, well, during this expansion, the gas does less work than it does in an isothermal process. So this is something we can calculate. So first of all, for the isovolumetric part, well, there is no change in volume, right? Delta V is equal to 0. So what's that tell you about how much work is done? It seems like it's, well, 0, okay? So the amount of work during that part is 0, and also, well, that vertical line, there is no area under that curve, okay? So there's nothing we can actually calculate there. Again, if it helps a little bit, think about what the gas is doing at this point. We're keeping it at the exact same volume, and the pressure is going down. If that's true, you've got the exact same container of gas, we're not moving the piston at all, but the pressure is dropping. Does that tell you anything about the energy in the system? Pressure is coming from molecules hitting the outside of the container. If the pressure is higher, they're hitting more and with more energy, and if the pressure is less, they're hitting less often and with less energy. Does that tell you anything about the temperature of the gas? Seems like it's dropping, right? So during this part, we could say that the temperature drops. And look at that. So I started to write drowsy, apparently. Like, I don't know what's happening there. I want to write drops. Temperature drops during that part of the process. Did I hear a question? No? Okay. During the second part really isn't that hard. We're going to use this same equation. Work is equal to the integral P dV. Except this time, since it's an isobaric process, P is constant, which means there's not a whole lot to do here. So that's just going to be P times, well, you could call it VB minus VA, or just P times delta V. So the pressure is constant. It tells you something about the height of that rectangle, and delta V is just the width of the triangle. It's just the area of that particular box. So the total amount of work getting from point A to point B in this case is just 0 plus this P times delta V, and that is less than what we got in the isovolumetric case, or excuse me, the isothermal case. During that second phase, the pressure is staying the same, but the volume is getting larger. What has to happen to the temperature there? Same pressure, even though it has more space in which to act. The only way that can happen is if during this phase temperature increases. And I think that makes sense a little bit since we dropped under the isothermal curve, right? We went down in temperature and then back up to get to the exact same temperature at the end that we started at. Okay? Pointing out the last slide and this slide brings up a couple of different things that you can see there at the bottom. First of all, of course, how much work is done by the gas is going to be dependent on where you're starting and where you're ending. That's going to matter every time, okay? But what also matters is how you get there, the path or the process or the combination of processes used to get from point A to point B. The amount of work is done based on the initial and final conditions as well as the path taken to get there. Also, how much heat is added or removed is based on those same things as well. In this first case, well, if it was isothermal, no heat went in or out at all anywhere during the process. But here we had heat exiting and then going back in. There was a change in heat during the process as the temperature decreased and then increased again. So work done, both W and Q, are dependent on the initial and final states as well as how you get between those states. Okay? Who's got thoughts? Yes.
Can you explain one more time about the temperature increase for isobaric?
Sort of imagine the gas molecules, once again, moving around. They're hitting the walls of the container. But now all of a sudden, they're given more space, which means in order to keep the pressure the same, I need to make sure they have enough energy to hit the walls of the container the exact same amount as before, even though where they're spread out more. The only way to do that is to add some heat and increase the temperature. Anyone else? Yeah. No work is done by the gas or on the gas in the isovolumetric. Energy has to leave the gas, but the process itself, you can imagine what I have is just some gas in a container, and maybe we just wait a little while for some heat to leave the gas, in which case I'm keeping the volume the same, but the gas itself is less energetic now, so it's exerting less pressure. You people are going to hate me in like 2 more weeks. Someone out there said, I already hate you. Thank you. I appreciate that. Let's talk about one additional process before we move on to the last few things in this chapter. This is something known as a free expansion. A free expansion. Notice it's described as a type of adiabatic process where the gas is allowed to expand in volume but not doing any work. No work, even though it expands in volume. So what we have is essentially some gas that's trapped in a container, and instead of making it, say, push on something to take up more space, we're just going to remove all restrictions and just say, hey, here's some more space. Feel free to expand into that space if you'd like to. And of course, it's going to like to because it's a gas, and all of those energetic contained particles are just going to expand to fill whatever volume you give them. Okay? So in this case, first of all, if it's adiabatic, we know that Q is 0. Okay? That's the definition of an adiabatic process. But now we're saying it's not doing any work either. So the work is also 0. Which means that according to the first law of thermodynamics, what else is true? Yeah, the change in internal energy is also 0, which means that what is constant? Temperature, right? Internal energy is directly proportional to the temperature. So we can say in this case the temperature of the gas is a constant. So what is the point in this whole type of process? I bring it up because you might see it in the homework. You just never know. A couple of different things. This is sort of an experimental procedure to test whether what we just said is completely true. To determine that if in the case of a real gas, if it's really true that the internal energy is just dependent on how much temperature the gas has. Okay? And it turns out that if you actually do this experiment, you can detect a really slight change in temperature, which means that, again, real gases are not ideal gases. They don't behave exactly as we might predict. So there's a slight temperature change, which means that this internal energy has a slight dependence on pressure and volume. We're not going to discuss that slight correction. Okay, I just want you to know that that's something that might be involved if you decided to further yourselves in this field and dealt with more complicated situations. The internal energy is dependent on temperature primarily, but there is a slight pressure and volume dependence, as we can see in the case of a free expansion experiment. Also, there is no way for us to actually draw a PV diagram for this because this is not a quasi-static case. As soon as I release that and the gas starts expanding, different parts of the gas are going to be at different pressures, and, well, it now has a constant volume, but I don't know what the pressure of the gas is because it's a bunch of different pressures. It's not a quasi-static condition. All the intermediate states aren't defined, so I really can't even draw a PV diagram. Just keep in mind that this is sort of something else that's out there. We're not going to do a lot with it, okay? Which sort of brings us to the end of the first law of thermodynamics for now. Does anyone have any questions, comments, thoughts? Coffee. How'd that word slip in there? Okay. Earlier in this chapter, we dealt with specific heat. Specifically, yeah, that was funny. Laugh. I didn't even mean to do it. Yeah, thank you. That was one of those lying laughs, wasn't it? Yeah? Okay, I appreciate it. So we specifically talked about the specific heats of liquids and solids, okay? We looked at phase changes, we looked at latent heats, we did all of that sort of stuff and saw how heat is related to temperature change and phase changes. What we didn't really do is talk about gases when we were doing that discussion. Like, sort of the problems tailed off when we said, like, something could turn into a vapor, and then maybe you could put in more heat and it would increase in temperature, but we didn't talk about that part of it at all. So for this slide and the next few slides, we're going to focus on the specific heat of gases. And let me point out that it's not just dependent on temperature. It's dependent on the process, whether I have a constant volume as I change the gas from one state to another, or whether I hold the pressure constant. So we're going to have two different types of specific heats for gases. So let me give you these equations, and then we're going to talk about them a little bit. They look similar to what we had before, but things are a little bit different. So we're going to say the heat at constant volume is equal to N times CV delta T. And the amount of heat at constant pressure is equal to NCP delta T. So this is for constant volume, and this is in the case of constant pressure. CV and CP are the molar specific heats, and we can get those back in terms and units of things that we had before with specific heats by following this process. We could say that CV is equal to the mass over the number of moles times the regular specific heat, and CP is the mass over the number of moles times the regular specific heat at constant pressure. We're using molar specific heat here, which puts it in terms of different units, because there's some stuff in this diagram below that we want to point out. The numbers work out in an interesting way that relates to energy. And if you're wondering what molar specific heat is, it's just like the definition before, but now this is the heat required to raise 1 mole of gas by 1 degree Celsius. So take a look down below. Notice this table is broken up into 3 segments. 3 different types of gases: monatomic, diatomic, and triatomic. Okay? So we're going from more simple gases to more complex gases with more atoms per molecule. Take a look at the center here, the molar specific heat at constant volume and at constant pressure. Notice if I look at the 2 monatomic gases they gave me, the numbers are, well, the same for both of them. Okay, we get 2.98 for CV and 4.97 for CP, no matter what the monatomic gas is here. We could list other monatomic gases. You're going to get the exact same numbers. If I step down to diatomic, well, they vary a little bit more, but they're still roughly coming out to the same value. And then they diverge a little bit more as the molecules get more complicated. Okay? But what we can essentially say is that CV and CP are essentially the same as long as you're dealing with gases that have the same number of atoms per molecule. Okay? And we're going to look at some derivations that show us why this is true, all based on our favorite kinetic theory from chapter 18 once again. Okay? Kinetic theory, just again remember, just means a bunch of molecules moving in all the random directions at a variety of temperatures or a variety of velocities that are given by the Maxwell distribution. Okay? So we're going to use kinetic theory and combine it with the first law of thermodynamics from this chapter and try to determine that, in general, how much these 2 quantities should be different, what the difference between CP and CV should be. So we're going to look at 2 processes. We're going to start with constant volume. In other words, the change in volume is equal to 0, which we know when there is no change in volume, work is also equal to 0. So we can use the first law of thermodynamics and say that the change in internal energy, which is equal to Q minus W, well, the W is 0, so this is just equal to Q. So in other words, you could read that as any change in internal energy is happening because I've added or subtracted heat. It has nothing to do with whether work is being done on the gas or work is being done by the gas on something else. In a constant volume process, all the change in internal energy is about heat being added or removed. So I'm going to take this and give that Q a subscript V, just to remember this is the amount of heat that was involved in the constant volume process, and say that that's equal to the change in internal energy. We're going to use that again in just a second. Since we're trying to compare CP and CV, I need to look at the other constant process as well and look at constant pressure. Constant pressure. In the case of constant pressure, we could say that Q in constant pressure is equal to the change in internal energy plus W. Again, from the first law of thermodynamics, we've just rearranged it. In the case of constant pressure, work is being done and temperature is changing. Both of these are happening if you just go back to a couple of slides and see what we said back there. And now let's assume that for these two processes, we are going to have the same change in temperature. And let that link the two processes and see what we can determine about the difference between them. Let me change one thing here on this line. Delta E internal plus work. We know that work is P times delta V. So let's put that in there as well. So we're going to use this equation and this equation and put them together and see what happens. So we can say that QP equals delta E internal plus P delta V. And we're going to take this and put it in right here. So now we have QV plus P delta V. And then I'm going to bring that QV to the other side. QP minus QV equals P delta V. So now we're starting to get where we're trying to. The QP minus QV is the difference in the amount of heat required in these two processes for a certain volume change. We're trying to go from there to the difference between the molar specific heat. So once I have this and the two equations from the previous slide, we should be able to get there at this point. So let's see. For starters, I'm going to use the ideal gas law. So PV equals nRT. And we will rearrange that to say that delta V is equal to nR delta T over P as long as we have a constant pressure, which we're still working with this second case. So we do have a constant pressure in this case, and we're going to plug that in to that equation. So let's see. In that particular case, what's going to happen? The P's are going to cancel out, so this is just equal to nR delta T. Let me make sure I didn't make a mistake. Everything looks good. So let's take this and go up here, and we've almost got what we're looking for. So for QP and QV, I'm going to substitute in the equations from the previous slide, all right? Which means we're going to have N times CP delta T minus N times CV delta T equals NR delta T. And then a bunch of stuff cancels out, and we've got the result we're looking for. So the N's are gone, and the delta T's are gone, and we've got CP minus CV is just R. Which is weird. The difference in the molar specific heats at constant pressure and constant volume is just equal to the ideal gas constant, which in terms of the variables we're using is just 1.99 calories per mole Kelvin. That 1.99 is the number we saw on the previous slide. I didn't show you that column, but if you calculate the difference between CP and ZV for a monatomic gas, it always comes out to be 1.99, which is R in terms of these particular units. Strange, okay? We're going to take this a little bit further, though. The difference in the molar specific heats is just 1.99 if we're dealing with a monatomic gas. All right? Does anybody have any questions anywhere in that particular derivation? We used the kinetic theory and the first law of thermodynamics to try to get to that. And it agrees with what we see in the table, which is the number we see experimentally. Okay? So, we know the difference between CP and CV, but we can also use the kinetic theory and the first law of thermodynamics, and this one is shorter, to figure out what the molar specific heat should be for a monatomic gas and make sure that agrees with the table as well. So, if we are dealing with a constant volume process, so for constant volume, we know that the change in internal energy is just equal to Q. We saw that on the previous slide. And for an ideal monatomic gas, we can pull something from earlier in this chapter, actually I think it was last chapter, and say that E internal is equal to the number of molecules times the average kinetic energy of those molecules, which we also said was equal to 3/2 nRT. I will let you go back in your slides to find those relationships. So we can take these two things. Delta E internal equals Q, which we know is equal to N times CV times delta T. And from before, we also know that's equal to 3/2 nR delta T, combining those relationships. And then we'll cancel some stuff out, and we get an equation for CV. So the N's are gone, and the delta T's are gone. So CV, the molar specific heat for constant volume, is just 3/2 R, which in terms of the units we're using is 2.98 calories per mole Kelvin. And again, take a look at that 2 slides ago. 2.98 was exactly what we saw there. Okay? So the numbers that we get experimentally that are in this table agree with the first law of thermodynamics and kinetic theory. So all of these assumptions we've been making about gases, they seem to be legit. Okay? The equations give us the numbers that we see in experiments. All right? So, what are we going to do with this? Notice, on this table, let me go back here. We said that this one is 2.98, but as we go to diatomic, notice, well, it increases a bit. And as we go to even more complex with 3 atoms per molecule, it increases more. Why is it a different value as we have more complicated molecules? Well, we've got an explanation for that. Why does it increase with the number of atoms per molecule? It is all because of the degrees of freedom. Degrees of freedom is defined as the number of independent ways a molecule can have or possess energy. The number of ways that it can possess energy. So E internal has some options. We can have translational kinetic energy. This is the one we've been focused on the entire time. This is 1/2 mv squared average. But things can have other types of kinetic energy, right? There's other types of motion. They may not just be moving from place to place, and I hinted at this before. We could also have rotational kinetic energy. I can't really have that with a single monatomic atom. It's just like, well, there it is. It can move around, but there's not a lot of rotation that's possible. And if there is, the moment of inertia isn't very high, so that's not going to be a lot of energy anyway. But once I have 2 atoms in the molecule that are bonded, that whole structure can rotate in different ways and have its own kinetic energy. But also, it's even possible to have what we might call vibrational kinetic energy as the number of atoms per molecule increase, because it's possible maybe for them to change the distance between themselves just a little bit and sort of act, you can kind of think of it as them being attached by a spring and them oscillating back and forth just minutely. So the number of independent ways a molecule can possess energy goes back to whether it's possible for it to have translational kinetic energy and rotational kinetic energy and vibrational kinetic energy. Okay? So we could say that with a monatomic gas, Well, the only option is it can move in 3 dimensions. Which means it's possible to have 3 different translational kinetic energies. So we could say that there are 3 degrees of freedom. Or in other words, maybe 1/2 mvx squared and 1/2 mvy squared and 1/2 mvz squared. Okay, so a monatomic gas, that's all it can do. That's the only type of energy it can possess. It has 3 degrees of freedom. It turns out that if we step that up just a little bit and went to diatomic, it has the same 3 translational directions plus 2 possible rotational axes. And you can see these illustrated there below. 2 different rotational axes. So for diatomic, we have 5 degrees of freedom. And those 5 degrees of freedom means it's possible for it to have energy in different ways. So we get a higher molar specific heat because if I want to change its temperature, I've got all of these different ways it can possess energy. I have to, put energy into all of these different compartments, if you want to think about it that way, to actually result in a temperature change. 5 degrees of freedom. So, we can take this a little bit further on the next page, and this idea leads to what's known as the equipartition of energy. Equipartition meaning we're just going to divide up the energy equally among the different degrees of freedom, whatever those happen to be. And it turns out that each degree of freedom gets energy equal to 1/2 K Boltzmann times T. So you'll have 3 halves when you have a monatomic or just the translational direction, 5 halves K Boltzmann T when we're dealing with diatomic and those additional rotational axes. And if everything was involved, and maybe we had vibrational things as well, you could even go to 7 halves times K Boltzmann T. And we see this expressed a little bit differently down below. It turns out that not all modes or all degrees are active at all temperatures. So here below we have a diatomic gas showing the molar specific heat at constant volume at different temperatures. So if I'm at relatively low temperature, you can see this is in Kelvin, so we're down below about 80 Kelvin. It turns out there's just not enough energy at that temperature for me to, say, fill up all the different modes of motion, moving in different directions translationally, and also to have energy available to rotate the atom itself, or rotate the molecule. But as I get to higher temperatures, so between 80 and about 1,000, well, now CV steps up to this higher level, because in that temperature I have enough energy to both move the molecules around and vibrate them. And then if I go to even higher temperatures, and we're getting ridiculously hot now, such that, even it says here that this diatomic molecule dissociates into 2 atoms at about 3,200 K, so they've just sort of extrapolated what's happening. But there, for a little piece of temperature, you can see that all the modes are active. There's enough energy at those temperatures to have motion and rotation and vibration, and each one of those modes gets an equal amount of the total energy according to this thing that we call the equipartition. Okay? This whole thing, if you wanted to study it a little bit more, is explained by quantum theory, which we don't do in this particular course. But the idea that you have to have certain amounts of energy to activate certain levels, the energy is quantized. You could deal with that in a quantum physics class, but we're not going to do that here. All right? There are 2 things left in chapter 19. It is 2:53. We are going to be done early again. Doesn't that make you a little sad? What is cheering? You owe me coffee. That's how it works. So, a couple of different things here to wrap stuff up. First of all, I agree that this is in a little bit of a weird place. We're not going to talk about the details of adiabatic expansion a whole lot. In fact, we already know what it means. But I want to let you know that there is an equation that helps describe this process. And it's not that PV is equal to a constant, but rather PV raised to the power of some other value. So we'll use gamma up there. And you can just look up different gamma values for different gases that are adiabatically expanding. So I don't want to talk a whole lot about that. I just want to give you that equation and let you know you can use it in homework, and we're not going to derive it or anything, all right? Q is equal to 0, and PV to the gamma is equal to a constant. You can look up those values. Which brings us to different types of heat transfer, different mechanisms for this energy to move from one thing to another. Part of this is going to be qualitative, just sort of understanding how the process works. Two of these different heat transfer processes, we've got an equation that you can use to actually calculate the rate of heat transfer as it moves from one substance to another. So first of all, we've got the idea of conduction. Conduction requires some physical contact, and it's literally transferring heat between substances because of collisions. There's actual physical collisions, and one molecule hits another molecule and gives up some energy to the other one through physical contact and through molecular collisions. So, of course, we know that this always happens from something that's warmer to something that's cooler. Well, it's simply because there's more molecules with more energy moving around on the hot side that are going to hit the slower moving molecules, transfer them some energy, and that sort of just chain reacts into the cooler region. So conduction always goes from hot to cold, and we'll see that in a little bit more detail in the next chapter when we're dealing with some more laws of thermodynamics. So we can't get any transfer unless we have a temperature difference. So we could say that this requires a delta T. And we can also say that the rate of heat transfer is equal to a constant K known as the thermal conductivity times the cross-sectional area that it's flowing through times T1 minus T2 over the distance through the material that this heat transfer is happening. So you can see A and L and T1 and T2 all illustrated in the diagram there to the left. So notice a few different things matter and affect how fast Q transfers, what the rate of heat transfer is. It's not just about the temperature difference between the two materials. It's also about the materials themselves, or the material itself in the middle, the thermal conductivity, which tells you something about how well that material can transfer heat through it. But it's also about the dimensions of the thing that's transferring the heat. Is there a large cross-sectional area? If there's a lot of area through which the heat can flow, well, you're going to get a faster rate of heat transfer. I think that makes sense. But also, if it has a long distance through which to travel, well, then the rate that the heat transfers from one thing to the other is going to be lower. And I think that A and L sort of makes some logical sense, okay? Thermal conductivity, you can see some values there on the top right. Air, not terribly thermal conductive, but things that are metallic tend toward having better thermal conductivity, and I think that we all sort of know that, right? This explains why if I touch something like a piece of copper, it feels cool to the touch. That's because it can readily transfer heat out of your hand, and you detect that as it feeling cool because it's taking heat away from you. But if I touch something else like, wool down there, the bottom there, I touch it, it doesn't feel cool to my touch because I touch it, and it doesn't readily take heat out of my hand, okay? So the different thermal conductivities of material tell me something about how they're going to feel based on how well they can transfer heat, all right? Conduction, I think, is the obvious one. Maybe? Yeah. I'm sorry? If L equals 0, we have no material that we're even examining or passing heat through. So the equation at that point, well, it's undefined and makes no sense at all. We've just got two temperatures and nothing connecting them. Okay? Anything else about conduction? We're going to talk about conduction later in the class, electrical conduction. So keep in mind that there seems to be some sort of connection between thermal and electrical conduction because, well, metals are pretty good at both of them, all right? The second method of heat transfer is convection. And this one we experience all the time, but it's a little bit more esoteric because it's just not as obvious as like molecules are just hitting other molecules and transferring their energy. Convection involves mass that's moving from one place to another. And I think probably all of us have at some point used a convection oven. That's just the standard oven that you use to bake your frozen pizza. Yes? You don't eat frozen pizzas? Listen, I'm 44 years old. I eat frozen pizzas. I will readily admit that I eat frozen pizzas. So you eat frozen pizzas as well, right? Yeah, I thought so. Anybody for Pop-Tarts every morning? Yes, I also eat Pop-Tarts basically every morning simply because it's easy. And I just, at that time of day, I just need food and coffee. Having to actually put that together is a problem. What flavor? That varies a little bit. I generally don't go with the more desserty ones. I try to fake myself into like eating healthy by saying it's got strawberries in it. Or cherries, or what's the other one? I feel like there's a third one that I eat. Cherry, strawberry. No, I don't eat s'mores or chocolate or cinnamon. I might eat blueberry occasionally. I don't know. It's mostly strawberry and cherry. And then there's the debate of whether to have the frosting on it or not. Frosting. You want the frosting? I kind of prefer the frosting, but there's, again, something about not having it that it's like, I'm having a nutritious breakfast this morning. It has strawberry filling and no frosting. But compare the health facts on the back of those two boxes. The frosting one is actually a little bit better, weirdly enough. Like tiny, tiny little bit, like 20 calories or something. I think it's just because there's less dough on the frosting ones. Weird, I know. Anyway, I told you, I am a child. My wife is a child as well. So, she doesn't eat Pop-Tarts, though. She hates them. Anyway, convection ovens for the frozen pizza. What happens in a convection oven is much like what would happen if I decided to just build a fire here at the front of the room, which clearly I'm not going to do. If we did that and built a fire, the air nearby the fire would begin to heat up. And then because it's heated, it would expand in volume, becoming less dense. And then we know that, hot air rises. So, that hot air is going to be mass of air that's moving to higher regions where the air is cooler. And it's going to force that air down, which now it's going to get heated and rise. And we can eventually sort of get like circulation in the room of air. And that's all happening because literally molecules that are hotter or that are moving around more transport themselves to another place. It's not about the collisions. It's just about like hot air is here and now hot air has moved back there. Okay? Convection is about mass movement of gas molecules. So we also see this not just like in a convection oven, but if you just thought about wind and weather. Why do we have wind that's happening? Well, there's a variety of things that are going on to cause wind and air to flow from one place to another. But one of them is convection. You have regions that are hotter, regions that are cooler, and that's one of the things that makes airflow happen from one place to another on the Earth. So, convection. We're not going to talk about that really at all quantitatively. I just want you to be able to recognize what it is. But the last quantitative thing we're going to look at is radiation. And this is going to come up again in many chapters because radiation is the transfer of heat by means of electromagnetic waves. Once we get to chapter 21, we're going to start entering the world of electromagnetism, and we're going to go through electricity and cover all of that. We're going to go through everything dealing with magnetism and do all of that. And the last chapter that we do dealing with electricity and magnetism sort of combines the two, and we learn about how you can get waves that are a combination of electrical effects and magnetic effects. or electromagnetic waves. So at this point, we're just going to talk about the fact that, yes, they exist. We don't know how they exist. We're going to learn about it later. And they can transfer heat from one place to another. And there doesn't have to be a medium at all in between. And we know this is true if we just think about the sun, right? The sun heats the earth. There's nothing in between here and there. But there are electromagnetic waves that leave the sun and hit the earth, and we get some heat that occurs here on the earth because of that heat transfer that's coming from the sun without means of a medium. We have an equation for this. Again, the rate of heat transfer by radiation is equal to a new constant known as the emissivity. And I'll tell you more about that in a second, times a constant known as the Stefan-Boltzmann constant. And that is equal to 5.67 times 10 to the minus 8, and I'm not going to worry about the units, times the area. So you can see in some ways this sets up like the conduction equation. But then we have a little bit different because it's proportional to the temperature of the thing that's radiating to the fourth. So these quantities, again, this is the rate of heat radiated. And all of this stuff over here has to do with the thing that's radiating. The thing that's putting out the energy. First of all, the emissivity ranges from 0 to 1. And it is based on the type of surface that's radiating. We could say, first of all, that 1 is something that's typically really dark, like black. And 0 corresponds to something that's really shiny. Shiny. Just the word makes me think of something. TV show from early in your lives. But a wonderful show that only had, I think, 13 episodes that all of you should go watch tonight. Does anybody know what I'm talking about? Yeah. Well done. Firefly itself is quite a shiny television show, and you should all go enjoy it. I won't say any more. It makes me sad that it's gone, though. So very sad. So it turns out a couple of different things are true. First of all, something that is a good absorber, something that can take in radiated energy, is also a good radiator. And all things do both of these things. They absorb radiation or heat by means of radiation, and they emit radiation. All things do both. And a value of emissivity that you have for a given object applies to both its ability to take in radiation and give out radiation. So we're going to do one more thing here at the bottom of the slide, and then chapter 19 will be in the books, yay, by looking at two different objects and the object giving up energy through radiation and taking in radiation from something else. So let's say that the first object has a temperature T1, and there is something over here, some other object that has a temperature T2. And both of these are radiating. Okay? But we're going to focus on T1 and look a little bit about its rate of heat radiated based on how much it's giving off and how much it's receiving from the other object. So we could say that the net Q flow from object 1 is dQ dt is equal to its emissivity times the Stefan-Boltzmann constant times its area times T1 to the fourth minus T2 to the fourth. And the way we get at that is to say that for this one, dQ dt is essentially just equal to epsilon sigma a T1 to the fourth. And it absorbs proportional to T2 to the fourth, because what it's taking in is about how much the other thing is radiating. So we have to combine both of those, how much it's giving off minus how much it's receiving. Thus the subtraction here, where we essentially have both of those, a delta Q, delta T, for putting out energy and receiving energy to get the net energy flow for T1, or for object 1, based on its proximity to another object, object 2. And of course, you could flip that around backwards and talk about object 2 and just write it exactly in reverse, okay? T2 to the fourth minus T1 to the fourth, okay? And I think that's about all that I wanted to say. I'm scrolling down. I see no more notes. And I didn't give you guys chapter 20 yet, so I can't even start it. Or can I? You want to start chapter 20? There's a question. Hold on a second. Yes?
Is area relative between surfaces or like total surface area?
For the area here, we're specifically focused on object 1 and what its net gain or loss is. So I'm worried about its area.
So if it's like a spherical object or something,
Yeah. It'd be its surface area. Yep. Yes.
is that a delta Q, the delta T, is that temperature or time?
That should be time. My bad. It's a rate.
So, and then also like it's like a really like long rectangular object. And
Then it'd be maybe the effective area that's facing the other object. Yeah, it'd be more complicated.